So, hello everyone. Geometry will be starting today. Euclidean geometry. This is the first session. Euclidean geometry. All right. So, this is basically a recorded session. And regarding this Euclidean geometry course, I would like to first mention a couple of things. This course is not at all exam oriented. This is not exam oriented. It's good if you're preparing for any of ISI or CMI, Olympiads, JE. When I say JE, I mean J Advanced. Any of this. It doesn't really matter. It will help you in everywhere. ठीक है? The problems we'll be doing are gonna be of good level, great level, not basic. I'll make you think at that level. I'm not just gonna teach you about the theory, about the criterias, about the theoretical aspects, the theorems, and everything that's in Euclidean geometry that you study in your NCRT's 9th and 10th standard. I'm here to train you about the techniques that are required to solve extremely difficult geometry problems, to crack, to observe the patterns, to observe configurations and figure out what technique you're supposed to use in order to solve that problem. Such kind of problem appears in RMO, in INMO, USAMO. We'll be doing them. Apart from that, the only prerequisites that you require for this course is having a reading of NCRT 9th and 10th, the geometry chapters. If you know this, you're eligible for the course. If you don't, just go and read. Otherwise, you may feel like problems. I'll be assuming that you know this. I'm not going to tell you this is the criteria, this is how you prove using this criteria. No. All right. So let's begin the course. We're calling the course, as you saw, Euclidean geometry. So exactly like in the live class, let me just ask this. Why do we call this Euclidean? If you're calling this Euclidean, there must be something that is not Euclidean, right? So what is in Euclidean? What exactly are we going to do in Euclidean? What exactly do we classify as Euclidean? And what is non-Euclidean? And why exactly is this relevant? We know that Euclidean geometry is being used from centuries, from Egypt, right? They had to make the pyramids. They had to do a lot of construction stuff. The architecture is really good. Even in ancient India, if you see the architecture, southern temples in South India, they're so good. They must have used geometry, a lot of Euclidean geometry. But what about now? We have a lot of technology. We have advanced too much. Why do we still have to study triangles? Why do we still have to study circles? What's with all this? Why do we have to do Euclidean geometry at all? Why do we have to do such difficult problems, such difficult configurations, such difficult like proofs and stuff? Problems as in IMO. IMO is asking geometry. Why? We'll be looking into the application of this applications. What do we have today? So we'll be starting with a banana. For people who missed the live class, once again, I'm not really good at drawing, so please. What? Excuse me for this. I'm not really good at drawing. Okay, so this is a banana. Let's just say it's kept on your table, and it's easy for you to tell its shape. What shape is the banana? It's 2D, 3D, whatever it is. You can tell it by looking at it. It's 3D, of course. Is it curved? Curved inwards? You call it saddle like. Saddle means like this. If a surface is like this, we call this saddle. Alright. Curved outwards. Like you have the earth. Earth is curved outwards. Right. So you can tell by looking at it from outside. Now, I want you to take I want to take you to a second situation. I want you to think of an ant on a really long road. Let's just say this is okay. Let's just say this is the road. This is around, let's say, 200 kilometers. Here's the ant. We're calling her. Okay, let's not call her anything. She's traveling. She's just moving here on this road. The question is, will the ant ever know about the curvature of the plane it is moving in? This plane. Will the ant ever know about the curvature? This is really long. The ant is moving. We are looking at it from outside. We know it's curved. It's a bit curved. Imagine yourself at the place of ant. It's so small. Will it ever know it's curved? Like no, no, right? It will never know. Now you were able to tell that yes, it's curved. You were also able to tell that the shape of the banana, it's saddle-like, it's curved, it's 3D. Now, if you were a bacteria inside the banana, exactly like the ant on this highway, which is 200 kilometers long, if you're a bacteria inside the banana, this does not look like a banana. I know. Let's just say this is a banana. Assume it. We are studying maths. Just assume everything. All right. So you're a bacteria inside the banana. You're inside it. You're not watching it from outside. You're not looking at it from outside. You were able to tell earlier. You're inside. Will you be able to tell exactly like this ant? You wouldn't know. This banana would be the universe for you. Now come to real life. Let me just add a page. Perfect. Come to real life. You are this small. The universe is this big. You are exactly like the bacteria inside the banana. Right. You don't know how does the universe look like from inside. Exactly like the bacteria doesn't. The ant doesn't. The ant is smarter than you. She decided to do something. Alright. She's moving on the earth. Right? She's moving on the earth. Let's just make a earth. This is the earth. Let's just draw some latitudes and longitudes. These are longitudes. I did geography. Enough geography. I hope you have also done. Geography is a good thing to do. These are latitudes. Alright? Let's just say the ant started moving from here, this point, went here and here. A triangle, right? Alright, so there was a bit of interruption. So I was saying the ant is moving from A to B to C. If you see this this path, right? This is on the surface of the earth. If you look at the triangle from the top, it will look like a normal triangle. If you just move a bit to other sides, it's gonna look like this. Wait a minute. This is A, this is B. Are you able to visualize this? Why is it so? Because of the curvature. This plane is curved, right? Because of the curvature of the earth, the triangle is actually gonna look like this. The earth is curved outside, right? So now the ant knows from Euclid's geometry that angle A plus angle B plus angle C of a triangle should add up to 180. We all know that. What the ant found out was that in this triangle, let's just call this earthly triangle. In this triangle, what's happening is angle A plus angle B plus angle C is way greater than 180. Alright. Now now the ant got one of her friends, and they both decided to walk on these longitudes. You see this longitude? This, they were moving in straight lines. They're moving in straight lines. Both of them. They're parallel. But to their amazement, they just met in the end. They went on and on and on in straight line, in a straight path that was perpendicular to this. What is this? This is the equator. This is the equator. Both of these longitudes are perpendicular. All the longitudes are actually perpendicular to what? To the equator. According to Euclid, this makes them parallel since they are perpendicular to the same line, right? So if they're parallel, they should never meet. What they found out, they met. They met at the poles. This is the south pole. Sorry, this is the north pole, right? So they met at the pole. Why is it happening? Because of the curvature of the earth. If you imagine, if you just rotate the earth a bit like this, such that this longitude comes here. This is called the prime meridian, by the way. This one. So this one comes here. So you'll find it's a straight line. But still, they're meeting. Why is it happening? It's because of the curvature of the earth. You need to visualize that. I can't make you visualize, right? So she found out this thing. The ant made two observations. The first one was the angle sum property of the triangle was flawed according to her. The sum was coming to be greater than 180. Second one was parallel lines meet. The ant thought that Euclid is cracked. But we know that Euclid is not stupid, right? There must be something wrong that we are doing. We know that the plane, it's because of the plane. It's happening because of the plane. What Euclid has defined is for a plane surface, is for a surface that is not curved. If the surface is curved outwards like the earth, then the sum would be greater than 180. If the surface is saddle like this, saddle like, inwards, curved inwards, it will be less than 180. The triangle would be something like this. So when is it 180? It's when it's a plane surface. Now what about this? So the ant concluded that if it's greater than 180, my universe, the road I'm traveling on, is curved like this. If it's less than 180, it's like this. If it's equal to 180, then it's flat. This is something that the bacteria inside the banana can also use to know if the banana is curved is what, right? Saddle like or straight, like a cube or something. This is one of the things that we can also use to know how does our universe look like, to get an idea, to get a bit of idea. This is one of the criteria. There are a lot of intricacies that get used. I'm telling you in a extremely layman terms. So from this idea comes cosmic triangles that scientists use to know how does the universe look like. They just imagine, in like imaginary terms, they just assign different spots to distances as long as galaxies. They make triangles. We call these triangles cosmic triangles. They check if the angle sum property it's greater than 180, it's less than 180. This is not the only thing they do. This is like very layman. I'm just giving you an idea. All right. So that's how we know it. Now, what exactly is this? We refer this as, we study all this in Riemannian geometry. What do we study? What is it? It's kind of generalized Euclidean geometry. Euclidean. It's a lot more than that, but okay. For curved surfaces, one of the things. Curved surfaces. So we do all that kind of stuff when it's greater than 180, when it's less than 180. We do that in Riemannian geometry. Euclidean geometry, we have to deal with plane surfaces. I hope you have understood why are we calling this specifically Euclidean, and what differentiates Euclidean and non-Euclidean geometry. I hope it's clear. Now this was something that is not very important as per exams point of view. It's just to feed your curiosity. It's just to give you a purpose. Why do we study this stuff? Also, it has application, lot of application. You can look up to webs like video games and stuff. Lots of applications. I mean, they're not recruiting IMO people to do constructions, right? To do construction work, to make temples, to make mosques, to make stuff, you know. So yeah, making temples as good as those in South India is such a like great feat. I don't think people will be able to build something like that anymore. Anyways, let's just do this. I'll be starting the course with congruency. Most of the places it's angle chasing. I won't be doing angle chasing. It's because angle chasing keeps coming in all the topics. It's not something you can do in one topic. Alright. So it will appear in congruency as well, similarity as well, in area as well, everywhere. Like you'll see problems regarding finding angles. So it's not wise to do it as a topic. It's just something, it's just we're supposed to find a technique you can call. Alright. So congruency. What does make two triangles congruent? We all know that. But I want to discuss something regarding the conditions. The conditions, we have two triangles. Let's call them ABC and PQR. They're said to be congruent if and only if. This is if and only if. I'll tell you. First, if AB equals PQ, BC equals QR, AC equals PR. Moreover, angle A equals angle P, angle B equals angle Q, and angle C equals angle R. This is the definition. We're saying if and only if. This means if this happens, then we'll say congruent. If we are saying it's congruent, then this happens. Both ways. That is why we use if and only if. So these are the conditions. This is the definition. You don't need to prove definitions. This is something which is defined. Like we're gonna call somebody, like if somebody is orange, we're gonna call him Trump. It's like that. You cannot just ask for proof. You know it. You know their parents named them that way. So this is definition. These are characteristics. So if something like this happens, then we're gonna call it congruent. They choose congruent. We could call it anything. All right. So they were smarter than us. So we'll stick to what they used to call congruent. Now there's no proof to this, and these are called necessary conditions. These two that I wrote, these are called as necessary conditions. All right. Now there's something also called as sufficient conditions. What are they? It's essentially saying that if you prove a chunk of it, a small thing, it will imply that the big condition, that is the necessary condition, is proven. This is what sufficient condition is saying. That means this thing, let's say we have to satisfy 6 conditions here, right? For congruency we have to satisfy 6 things. This and this. 6 conditions. We are saying if you prove even 2 of these sufficient condition, which 2 or 3 will decide later, but 3 of those, 2 of those, then these 6 are already done. This will imply that these 6 conditions have been proven. That is what sufficient conditions say. Now sufficient conditions, I'm saying, these are also called criterias. If you know, if you're not able to grasp criterias, that is what we call sufficient conditions. We have SAS, ASA, triple S, and RHS. Then the difference between the necessary and the sufficient condition is that necessary conditions we don't have to prove. Sufficient conditions we have to prove. We have to first prove them. What is SAS? SAS is basically saying that if there are two triangles, PQR and ABC, I'm sorry, okay, and ABC, they will be called congruent if, let's say, PQ equals AB, PR equals AC, and the angle included between them. I'm assuming you know these criteria, right? That is why I said I'm assuming you read NCERTs. So angle P equals angle A. What is SAS saying? It's saying that if you just have this will imply that the third side is also equal, QR is also equal to BC, and the rest of the two angles are equal. That is what this is saying. If this happens, then the triangles are congruent. And what does congruent mean? Congruent means all those 6 conditions. We have only 3, so that means the rest of the 3 are also true, since we are saying they are congruent. Now why should I trust this? If somebody is saying do just this, that will imply everything is done. Why should I trust this? We need to prove SAS first. We need a proof for SAS. Like first prove it that if 3 conditions are applicable, then all 6 are also applicable. This implies this. Otherwise give me all 6. Show me all 6. That's only when I'll believe that the triangles are congruent. I'm not gonna believe this. So you'll have to prove. I want you to think of the proofs. These are 2 triangles, ABC, and then we have PQR. This side is equals to this to this, and this angle is equal as well. So it's like we have to prove SAS. We don't have to use SAS to prove that they are congruent. Please understand this. You have used this in school. Prove that triangle ABC and PQ are congruent by using SAS criteria. We are not doing that. Please understand the difference. We are questioning the criteria itself. We are saying SAS is not true. First prove that it is true. Why should I trust that if SAS happens then the triangles are congruent? So it's like we are given AB equals PQ, AC equals PR, angle A equals angle P, and we have to prove angle B equals angle Q, angle C equals angle R, and BC equals QR. From this to this. This is what we have to prove. Now look at these two sides, AC and PR. I'll just pick triangle ABC, move it such that AC coincides with PR, such that AC coincides with PR. So this is triangle PQR. I'll move ABC such that this happens. AC is equal to PR, so it will perfectly coincide. I'm just writing AC as well here. The point is single one, ABC. These two sides are equal. Yeah. We have to prove also this angle is equal. We have to prove angle B is equal to angle Q. This. And apart from that, angle C equals to angle R. What we have to prove, I'm writing in red. Alright. BC is QR. Perfect. What we'll do is, we can see it here, like these two are equal. I'm sorry for drawing it in red. It should stay in blue. Okay, so we'll do a bit of construction here. Why are we doing this? We want an isosceles triangle. How does the intuition for the construction come? We see these two are equal and we'll decide let's just make an isosceles triangle. We don't know anything if it will help or not, but we're just doing it for fun. We can see these two angles are given to be equal. That means PO, let's call this. PO is an angle bisector of an isosceles triangle. And an angle bisector of an isosceles triangle is also its median and altitude. Not all of them. If you drop an angle bisector from here, that one will not be a altitude or a median. Okay, it's only one of it, the one between the two equal sides. Yeah, so this will be 90 degree. This will also be 90. This will also be 90. Now can I say that BC cos, sorry, sin C, what will it be? It will be OB. Is that correct? Right. Similarly, QR sin R would be OQ. And similarly, BC cos C would be OR, and QR cos C would also be OR. Now from these two triangles, if you observe them, this side is equal to this side is common, right? And apart from that, we have this angle equal to this angle equal to this angle equal to this for being what? Isosceles. These two triangles are easily congruent, so we can say these two are equal, right? That means OB is equal to OQ. So we'll write BC sin C equals QR sin R. This is like visibly equal. So BC cos C equals QR cos C. I'm sorry, this is r cos r. We'll divide these two equations. This will get cancelled. We'll have tan c equals tan r. Can I conclude angle c equals to angle r? Now the weird thing about this is that no matter how good the proof looks, this is wrong. The proof is wrong. Why? Because we're using a very fundamental thing of Euclidean geometry. We're proving it using trigonometry. While trigonometry itself is a result of Euclidean geometry. We can use trigonometry, sine rule, cosine rule in problem solving. That's good. We cannot use them to prove the very fundamental concepts of Euclidean geometry. For they came from geometry itself. It's a result, these trigonometric ratios are a result of similarity. So this proof is wrong. What's the right proof? It was done, it's an axiom. It's called an axiom. SAS axiom. Axioms are universally true statements that are applicable in all the fields. So SAS axiom, it was proved using transformation. It's circle geometry, construction stuff. You can look it on YouTube. They use comparison stuff to prove their videos. Now using this was proved using all these things. Now using this, we rigorously prove triple S, ASA, and RHS. I'm not going into those. If you want to read, you can read page 42 to 46 of CTPCM, Challenges and Thrills of Pre-College Mathematics. All right, we'll get to spotting congruent triangle things, right? Spotting congruent triangles. What is it? What does this mean? Spotting congruent triangles. This is exactly the technique that you need in problem solving. How to spot those pairs of congruent triangle from absolute mess of figures. Like those diagrams are really weird. They're like intimidating. How do you even figure out that like those two triangles hidden there are congruent? And then extract information from the congruency and then use it to derive other stuff, to conclude other information that helps you to prove to solve the problem. So how do you spot that? We'll learn this through a couple of problems. So here's the first problem that I want you to solve. Alright, so this is the first problem that we have that you have to solve. We are provided with a triangle. You can pause the video and solve. Okay, let's just change the colors a bit. We're provided with a triangle ABC. Alright. We are provided that angle B is equals to 2 angle C. D is a point on BC such that AD bisects angle BAC and AB equals CD. We have to prove that, we have to kind of find BAC. Alright. So what do we do? You must be thinking of angle bisector and stuff. I recommend you to use what you have studied till now, congruency. And also we'll mostly try to solve our problems using synthetic geometry, unless we're not left with any other option than using coordinate bashing and trigonometric bashing and stuff. So yeah, we'll study those as like separate techniques: complex bashing, coordinate bashing, and all. So yeah, yes, this question. So how do you spot? First of all, we look at what we are provided. What information are we given? We've provided that AB equals CD, and more important than that, angle B is equals to 2 angles C. This is more important than you think. I'm telling you these things, a couple of more things that you need to know. Observations kind of things that you need to observe in the problems. That is how intuitions for constructions come. If something like this is given, something like AB is equals to 2 AC is given, something like AB is greater than AC is given, immediately you have to know that you have to divide something. Sides are given, you have to divide the sides. Angles are given, you have to divide the angles so as to make some equality. What does that mean? We're given that angle B is greater than angle C, is equals to 2 angle C. What does that mean? Angle B must be greater than angle C. So half of angle B is angle C. So we'll half this angle. We'll divide it. We'll make. This is how we construct. I'll use a different color. I'm not. I'll actually forget changing colors. So yeah. So now this and this. These are equal. Why? Because we bisected them. We bisected this angle. And since this one is angle C is half of this whole thing, so this equals this. Let's just say x, x, and x. What else do we get? Triangle PBC we got to be what? Isosceles. Apart from these two sides being equal, what else have we got from this isosceles thing? What else? PB equals to PC. We just solved the problem. I was talking about spotting. Observe. You need to observe. What do we have? AB equals CD. PB equals PC. What do we need? What do we need here? Two triangles being congruent. That is what we need. What do we need for a triangle? Like to write a triangle, we need three vertices, right? Three different vertices. That's how you write a triangle. Are we able to find here? A, B, P, B. B is common. We have A, P, and B. It must be some triangle. We have C is common here. We have C, D, and P. It also must be some triangle. Let's just look at in the like the diagram, the main diagram. What do we have? APB and CDP. APB and CDP. You see, APB and CD what? CDP. CDP. Let's just join them. CDP. All right. So we are saying these two are congruent. Do we have enough data? This side is provided that it's equal. AB is equals to CD. We found out this equals to this. And don't forget this angle included between them. When you have two sides, what do you look for? What are the possible criteria that you can use? Either it's triple S or it's SAS. So you look for angle between those two sides or the third side. If you don't have any information regarding the third side, we have the angle between them, they are equal, then yes, these two triangles are congruent. Now you have to write, when you start writing it, you have to write the corresponding parts in order. Like if triangle ABC, some random triangle, is congruent to triangle PQR, you cannot write ABC is congruent to QRP. No, that is wrong. You have to write corresponding sides, corresponding angles. All right. So we'll observe that here. We have angle B and C. We have AB first. AB equal CD. Apart from that, we have PB to be equal to PC. We can write this DCP. Can we? AB being equal to DC, BP being equal to CP, and angle B is equal to angle C, is it? Yes. So we can say that triangle ABP is congruent to triangle DCP. What do we get now? We concluded this from the given information of the problem. We just we got to this. Now we'll collect treasures in form of CPCT, the corresponding parts of congruent triangles. We had 3 things. Remember that in congruency we have 6 things. We get 6 things. So if they're congruent, we must get 3 more things. 3 more conclusions we should make. Let me just redraw the diagram. We have the triangle. Okay. That's okay. That's good. A. Okay. A B C D. A B C and D. Here we have this point P. We call this X, and this is also X. This has been divided. We had joined this. And what have we found? We found that triangle ABP is DCP. Let me just highlight them with a different color. We have triangle APB, APB and triangle DCP. Right? Now by CPCT, should TD be equal to PA? Right? By CPCT. That's an ugly color. Let's just change it. PA equals to PD. Right? We should find 2 more angles as well. Angle BAP equals angle CDP. Notice I'm following a pattern. B comes first, then A, then P. So C comes, the middle one comes first, then D, then P. So you have to write it like that. Alright. Otherwise you'll mess up. So what is BAP? BAP, this angle. This is equal to CDP. CDP. Remember that this is the angle bisector of angle A. So I can call this Y and this Y as well. Right? Now since we have this to be equal to CDP, so this becomes 2Y. Is that correct? Since we have PA equals to PD, PA equals to PD, this side and this sides are equal. So this is an isosceles triangle. Triangle PDA is isosceles, and that is why we have angle A to be equal to angle this small angle D. So this will also be Y since this is Y. Is that correct? Does that make this whole angle, this complete angle ADC to be 3Y? This becomes 3Y. Now notice in this triangle, in triangle A, okay, wait. Notice triangle ABD, this is extended. This angle, that is this angle is 3Y. This angle is 2Y. Sorry. This angle is Y. And this angle is 2X. By exterior angle sum property, 2X by Y should be 3Y. That gives you X equals to Y. That is an absolute gem. Right? If you look at the bigger triangle, this was what? X. This was 2X. This was 2Y. Now since X equals to Y, we got. So I can replace Y by X. So I can write this as 2X as well. So it's 2X, 2X, X. That is 5X. By angle sum property, that is 180. And that gives you 636. Now angle BAC. This one. Okay. I had already made the bigger triangle. Yeah. So I had to find this one only. So 2X. 2 into 36, that is 72 degree. That is the answer. I hope you have learned how to spot the triangle. It's not important for you to be able to solve these problems. There were people during the live class who were overwhelmed by the problems, who were saying, do it from basics. I'm not here to do from basic. Alright? You know the basics, you're aware of the basics, you're doing these problems have been designed to push your brain out of its comfort zone, right? So it's not necessary for you to solve. You should struggle a bit, you should see the solution, you should extract techniques from them, so that in future if you encounter the same kind of configuration in some other problem presented in some other form, you should be able to observe and recognize the pattern, the configuration, and use these techniques. If a similar problem appears again and still you're not able to solve, then there is issue. If in the classroom you're not able to solve these problems, it's perfectly fine for you. I was not able to solve when I was doing, so it's okay for you. We have another problem. All right, this is problem 2. Okay, wait. Yeah, this is problem 2. And once again, the technique of spotting congruent triangles. We have to use it, we have to apply it. Remember the first thing that I told you. Write every information that has been provided to you in the question as it is in point format. Alright, first write them. Don't invent information by yourself just by looking at some random diagram that you made. There were people in the live class who would just say that is perpendicular, like randomly. It's not given in the problem. I'm not in any kind of way putting them down. It happens. I'm just saying, write it down, stick to what information is provided in the problem. So in the problem, you may pause the video and then solve. We have an equilateral triangle. First thing, equilateral triangle ABC. Second, it is given that DA is equals to DB. Third, point E is also given so that angle DBE equals angle DBC. And fourth, BE equals AB. Lot of information we have been provided and we have to find angle E. This is, by the way, AB. Sorry, this is BC. Okay, now you can do. Yeah. So AD is DB. This is one info. And we have BE equals to AB. This is interesting. We have the equilateral triangle that would make all three sides equal. One other side is equal to these three. So BE is equal to AB means BE is also equal to BC and BE is equal to AC as well. Now what else we have? So from here we concluded that BE is also equals to BC and BE is also equals to AC. Is that clear? Sweet. Now what else do we have? Angle DBE, this angle is equal to this angle. Now you should be already able to spot the triangles. Already. You have this side equal to this side. This side, this side, this side, this side. Angle and this side common. Do you see anything? Now, now you need to construct a triangle. Let me just make the diagram again. I hope you have seen where the intuition for the construction comes. And you have already spotted the congruent triangles. Okay, this looks like an equilateral. Who cares? Yeah, so we have this point D. Yeah, D will join this. It's in the problem. And E there. And one more. Yeah, this is the problem. We have triangle ABC. This is D. And this is E. We saw this to be equal to this. Why? Triangle ABC is equilateral and this is equal to this, so this is equal to all three sides. We have also been provided that these two angles are equal. We should have the intuition to think that we need to join these two, and these are the two triangles that are congruent. Triangle DBC and triangle DBE. Are you able to see? It's good if you're able to see. You should be able to see this. How are they? We have DB is equal to DB, that is a common side. BE equals to what? BC, and the angle included, angle EBD equals angle CBD, right? So by SAS, congruency criteria, we have this. Now it's time to collect the treasures using CPCT. What treasures do we get? Do we get anything? Angle BED equals angle DCB. If we call this X, this will also be X. We got this, right? We'll also get DC equals to DE. DC equals to DE, right? Anything else? We'll also get BDC equal to this angle. That won't really help a lot, as you can see. That like, you'll develop that kind of thought process, like something is helpful or not, that intuition with like problem solving a lot of. Okay, that is not a very advanced thing that I just told. That is very easily observable. Okay, this is not useful. We'll skip that. So yeah, this angle is equal to this. Does that solve our problem in any way? It doesn't. We'll have to look for another pair. Do we find anything else? Do we have anything else? Have you used all the information available to you? First information was equilateral, we used that. Second information was what? This being equal to this. BE equals to AD. We have also used that. Third information was this angle is equal to this. We have used that as well. There was one fourth thing, that was AD is equals to DB. Let me just bring the diagram. Here. Perfect. AD is equals to DB. Shit. We haven't used this information. AD and DB. We'll have one more pair of congruent triangles. How? I want you to observe AD and DB are given. What's our goal? To reach some triangle here such that they are congruent. One more vertex we need. Do we? One vertex is already common. We need two more vertex. So these are sides of two different triangles. Don't look at ADB. Don't look at this triangle. Not at all. AD and BD both are sides of the same triangle. Right? Don't look at this one. Why? Because we have to find two triangles, no? So these must be sides of two different triangles. What are those? BD is aligned with this one, BDE. We're just guessing, BDE. And we have AD, we have ADC. Are they congruent? Let's see. So AD and AD are common. BD, no, AD and AD are not common. Okay. We have BE equals to AC. Do we? BE was equal to all three sides of the triangle, so we have BE is equals to AC. Right? Perfect. Okay. So what else do we have? What else do we have? We had this AD equals DB. We have got BE equals AC. So S we have got. We may have one A, as I told earlier, or one more side. What side is left? It's DC and DE. Are they equal? Is DC equals to DE? Yes, it is. DC and DE, how are they equal? We proved this triangle to be congruent to this triangle earlier, and by CPCT these two are equal. I have written this here, right? So by SSS, what else? We've got BEC, BED, sorry, BDE to be congruent with ADC. Perfect. BDE congruent with ADC, A, D, and C. That means by CPCT, angle BED equals to angle ACD equals to this XX. Now what? The triangle is equilateral, so this angle must be 60. So we have 2x equals to 60 and x equals to 30. We are done. First problem, we had to spot one pair of congruent triangles. Second problem, we had to spot two of them. Now, one really amazing approach that I discovered when I was solving this problem back then. So it's really amazing. You would love it. This is the triangle. Here, there's this line, one more, and we have E outside. Right. What I observed was, it looks like this part, this triangle DCE, it was like a paper here, and you turned it, and you just turned it, you folded it, like you make paper planes, right? Paper planes, you fold a paper. It's exactly like you folded it along BD, you just made a crease at BD, and you folded it such that point C reached there at E. Are you able to visualize this? You folded this part you folded, triangle DCB, such that it went there, and it became this ugly looking diagram. If you're able to observe this, what we will do is we'll unfold this paper. Here comes the idea of reflection, taking reflection. How are we going to do it? I'll just erase stuff. I hope you've noted that down. Okay, this is not a live class, you can pause. I keep forgetting. Yeah. So yeah, I'll this is good enough of a diagram. I'll just choose this and move on the other page. Do you have, oh shit, we don't even have a new page. Okay, so now we'll choose it and we'll move it. Yeah, sweet. Perfect. So we'll unfold it. We'll like we'll bring E back to C. What will happen? The triangle will transform to this. We're taking reflection along BD of this triangle BDE. So it will fall. E was here. E was here. It will come to C. ABC. E will coincide with C, and will be done. This is the diagram. That's it. What do you say? This is x. This is x. And 2x equals 60. X equals 30. Now, how do we know? If you're confused about how do we know if BE will perfectly come here and coincide with BC, it can come here as well. It can come inside as well. So we are provided that this angle is equal. So if you take reflection, you know the angle is preserved. Angle of incidence and angle of reflection, whatever. That is preserved. That is equal. So it will fall back to here. So our conclusion is Right. So we are right about this. So yeah, you got x equals to 30. I hope you enjoyed the session. And if you want to attend the live classes, because that those are so much better with a lot of discussion going on. There are people trying to prove SAS using SAS. Okay, I'm not putting them down. I'm just kidding. So yeah, you can buy the course. It's probably one of the cheapest one out there. Not one of the, it's the cheapest one. And like you get the complete Olympiad, not just IOQM, complete Olympiad stuff with that price. So you can buy, you'll get assignments, you'll get notes, proper notes. These are very written in like amazingly good handwriting, as you can see. So you'll get like different notes and assignments as well, daily assignments after the class is over. So you can enroll in the course. Thank you.